So my name is Quinn and my partner for this project is Jack, and this project is for Computer Science 444. So we did a numerical analysis, specifically numerical integration of air pollution. So some of our motivations. Air pollution is a major threat to the health and safety of humans. According to the World Health Organization, over 4.2 million deaths are a result of outdoor air pollution every single year. Further, according to National Geographic, air pollution often contaminates our water and soil, which can have a really big impact on agriculture. We chose this project because analyzing air pollution trends is the first step to being able to combat this problem. Further, we chose this project because of the immense collection of data on air pollution and its different forms. So now a little bit about our data source. So we picked a data set that had hourly entries of air pollution levels that were recorded at road level or street level over the course of a year. So the air pollution levels were collected at road level in an Italian city between 2004 and 2005. So for 1 year. And multiple measures of pollution were taken at this road. Such measures were benzene concentration and NOx concentration. So the data was collected by the National Agency for New Technologies, Energy, and Sustainable Economic Development. And then it was distributed by the University of California, Irvine's Machine Learning Data Repository. So the webpage and some more information on this data can be found at that link there or at the link in the citation below on the screen. So here's kind of a closer look at the distribution of our data. So here you can see some of the different measures that were taken in this data set. So you can see that NOx concentration measure there and a couple others of the different metrics that they took, just to kind of give you a general idea of what this data looks like and the variety of data that was there. So here's kind of a specific example of what exists in our data. So this is looking specifically at the type of pollution RH. So here you can see that this has a range, a minimum of 9.2 to a maximum of 88.7. And then on the right, you can see the head and the tail of that data. So starting in that March of 2004 and ending in April of 2005. So now we'll talk about the numerical analysis methods that we used. So the first method that we took a look at was the trapezoid method. So here you can see the theorem for the trapezoid method. So the trapezoid method divides the x-axis into subintervals of n and then finds the areas of those trapezoids to estimate the integral. So again, you can see that formula there that we used in our implementation.
In addition to the trapezoid method, we use the Simpson's rule and compared the two. Again, on screen is the formula for the Simpson's rule. As you notice, it's pretty similar to the trapezoid rule formula, which is why we thought the two would be like decent to compare, as they both use similar calculations, similar ideas of dividing up into intervals and estimating the area of those to come up with a good estimation, essentially based off of your discrete data points. So those were the two methods that we coded and used to analyze and compare against one another. We'll take a quick look at the implementation of these methods. First, we imported our data using Python. We're working in Jupyter Notebook. We imported the data into a pandas data frame, cleaned and parsed the data. It was based off comma separation, so it was pretty straightforward. We made a combined date time field of the date time type, so that information was together instead of in two separate columns with strings. We converted the missing data to none data type. Missing data in the original data set was pretty sparse, but where it occurred, it was represented by a -200 value, which would have really thrown off our analysis. We just converted it to a none type. So our Python methods could accurately handle that because they understand that that means there's no data there. And then we printed histograms of the data to kind of see an initial distribution, which is what Quinn shared earlier, so we could kind of understand what our data look like. This is our actual implementation of both the trapezoid rule and Simpson's rule. Both of these methods took in a list of data points as well as the delta analyzed. So the original set of data points over the course of the day, including midnight on both ends, was 25 data points with a delta of 1. The data was taken every hour. As we got into trying to analyze the accuracy, we split the data in half over the course of the day. We used a delta of 2. But it just goes through here and sums up all the points according to the rules as given, kind of the sums and the methods as we discussed earlier. Our accuracy metric was kind of difficult to come up with because no true data for air pollution exists. All we have is these hourly measures. There's no truthful measure that was telling us exactly what they were, which is often the case for real world data collections, which is why we kind of had to improvise and try to come up with a good way to analyze these methods. So we split our data in half. So we integrated once using both Simpson and trapezoid rule with all the data points over the course of a day, 1 every hour for the 24 hours, and then add in midnight for the next day to get a full set. We had 25 data points. We considered this our truthful result. We also integrated using both the trapezoid and Simpson's rule with half of the points, every other data point, so essentially all the odd ones to test. And we compared those two values to see which was closest to the full results and therefore a more accurate method. And then by analyzing that similarity, we're able to find the more accurate method. So now we'll take a look at our results and conclusions and see which one worked out better for us. So here we can see an example of our results. Both standard deviation and error were lower for every case analyzed for the trapezoid rule when compared to Simpson's method. In the graphics here, we can see the NOx concentration here on the left. In addition to the standard deviation being lower, it has a lower error rate. So when you do integration with just half the points, so 13 instead of 25, it had an extremely low error rate. Simpson's rule also was lower, but it was still several times higher than the trapezoid rule. We can see that in both cases on the left and the right. 4 more cases, all of these have a much lower error rate for the trapezoid rule than Simpson's rule, which leads us to the conclusion that the trapezoid rule is much more accurate. Therefore, we can provide this recommendation through analyzing the results of the experiment, through the accuracy of the sums of total data pollution over a year-long period provided by both the trapezoid rule and Simpson's rule. We've concluded that the trapezoid rule provides a more similar set of sums and therefore greater accuracy and precision. We recommend using the trapezoid rule for further numerical integration applications.
So now some conclusions and future work. Air pollution is a major problem that the entire world is facing that we need to address. So being able to quantify the amount of pollution that's recorded is really important to evaluating the efficacy of policies to understand this issue. So to make sure that those implementations are being effective in reducing this air pollution. This analysis could be continued by analyzing data from other countries or even other years. Taken at this same street level. Further, in the future, additional numerical integration methods could be introduced to the program to ensure that the trapezoid method really is the best method to be evaluating this and making decisions off of. So here are some of our sources. You can see our data and where we got some of our information on air pollution. Thank you.